Hi everyone. We are going to continue our discussion of probability in 7B. We're going to look at two sections. The first one is independent versus dependent events, and then the other one we'll look at later. Okay. All right. So we need to do some definitions. What are independent events? Well, here's the definition. Independent events. Two events are independent if the outcome of one does not affect the probability of another. For example, if you roll a die twice, the outcome of the first roll does not affect the outcome of the second roll. Same thing with other things. So when one does not have an impact on what happens the next time, then that is independent. Some other examples that we've done in class are, well, we flip coin. We have drawn a card from a deck. Okay. We did an example about the number of girls in a family. So the gender of children. Just because you've had a boy doesn't mean that you're not going to have a boy or anything of that situation. Okay. So what if we're looking at two independent events and we want to find the probability of event A happening and event B happening? So the probability of independent events. If A and B are independent events with probabilities P of A and P of B respectively, then we can calculate the probability that both A and B occur using this formula. The probability of A and B is the probability of A times the probability of B. And note this can apply to any number of events. If you have three events, the probability of A and B and C would be the probability of A times the probability of B times the probability of C. Okay. So let's look at something that we have looked at before, which is the equally likely outcomes resulting from the roll of two dice. Now we looked at this and we created a probability distribution table for the sums. But first of all, we're just going to look at the chart and find the probability of 5 and 5. That means that the first one is a 5 and the second one is a 5. Well, there's only one way that can happen. So the probability of that event, just by looking at the chart, is 1 out of the 36 possible outcomes. But we can do this same thing by looking at the probability of the individual events. So using the formula, the probability of 5 and 5, well, let's look at the probability that the first die lands on a 5. Okay, so the first die lands on a 5 are these here. So that probability is 6 out of 36. There are 6 ways that can happen out of the 36 possibilities. Okay. Then we're going to look at the probability that the second die lands on a 5. Well, if I look here, those are these here. So that probability is also 6 out of 36. Now from here, there are a couple of ways that you can do this. You can just multiply this in your calculator. Or if you want to do it more manually, you can say, all right, well, 6 out of 36 is 1 over 6 times 1 over 6. This means it's 1 times 1 divided by 6 times 6, which is 1 over 36. Okay, So you can see that if we have a chart and we can see it specifically, that's one thing, but if we're going to have to use a formula, then we can do that as well. Okay. All right, well, I'm sorry, I paused there. I kind of got lost for a second. All right, so let's look at person A and person B, and they each flip a coin 5 times. Person A lands heads, 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 all heads. Person B lands heads, tails, tails, head, tails. So when considering every possible 5-flip combination, which combination is more likely to happen? The probability of all heads or the probability of head, tails, tails, head, tails? Okay, well, if we were in class, I would ask you, well, which one do you think is more likely? Okay, looking at the theoretical probability of this. Well, let's see what it says. Okay, so the probability of all of these, we know that the probability of heads, this is going to be the probability of heads times 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 the probability of heads. Well, what does that give us? In a single coin toss, the probability of getting a heads, there is one way to do that out of the 2 possible outcomes. Okay. The next toss is independent. It doesn't matter what happened on the first one. So this is 1/2. This is 1/2. This is 1/2. And this is 1/2. And if you multiply all those together, 1 times 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 times 2 is 32. Well, let's look at the second one there. This is the probability of heads times the probability of tails times the probability of tails times the probability of heads times the probability of tails. Okay. Well, we know what each of these is. So this is 1/2. The probability of tails, there's one way to get a tail out of the 2 possible outcomes. 1 out of 2, 1 out of 2, 1 out of 2, and this is also 1 out of 32. Now, just instinctively, I would have thought that the probability of this would be more likely. But when you're looking at the theoretical probability, they are equal. Okay, so what is the probability that person A flips a tail on the 6th flip? Okay, well, that's the probability, that's the P of T, which again, there is one way for that to occur out of the 2 possible outcomes. What is the probability that person B flips a tail on his 6th flip? Once again, that's the probability of T, which is 1/2. Now, this kind of leads into these independent events, into the gambler's fallacy, which is the mistaken belief that a streak of bad luck means that a person is due for a streak of good luck. Okay, just like in gambling, every time you play a different hand of cards, or every time you place money on a roulette wheel, or something as simple as flipping a coin, what happened in the past has no bearing theoretically on what happens in the future. So those are independent events. Okay. All right, well, now let's look at dependent events. Okay. Dependent events Okay. 2 events are dependent if the occurrence of one affects the probability of the other. So this means that the what happened the first time impacts the outcome for the second one. So the probability of two events, A and B. For two dependent events, we calculate the probability that event A occurs and then event B occurs by using the multiplication principle as follows. But there's a twist to it. If it is dependent, the probability of A and B is the probability of A times the probability of B given A. Now we're going to illustrate this by doing a game of drawing tiles. So, and we're going to do this in two methods. In both methods, two blue and two yellow tiles are placed in a bag. Okay, so I've got a bag, a blue, blue, a yellow, yellow. A tile is drawn from the bag. The difference comes when replacing that tile or not replacing the tile before drawing a second tile. Okay, so let's look at replacing the first tile, method 1. Okay, so if you are looking at this and you want to know, we've got to do, the outcome is going to be the probability of the first draw times the probability of the second draw. If we replace the first tile, then we'll see what happens. On the first draw, it makes perfect sense. Okay, we have two opportunities to get a blue out of the 4 total possibilities. Same thing with the yellow. There are 2 ways to draw a yellow out of the 4 tiles. Okay. Well, let's now look at the second draw. The second draw, the bag remains the same. We have taken this and we have put it back in the bag. So the bag has 2 blue and 2 yellow. So the probability of a blue is there are still 2 ways out of the 4. A yellow is 2 ways out of the 4. Same thing here. 2 out of 4, 2 out of 4. Okay. Okay, so if I look at these, if I list the probability of a blue or a yellow on the first one, that's going to be 2, whoops, wrong pen, 2 over 4. And then we look at the second draw, the probabilities of a blue, yellow, blue, or yellow. And once again, that's 2 out of 4 on each of these. So if we do the multiplication on this, we see that gives me 4 over 16, or 1/4. And since the fractions are the same on all of these, the probabilities are going to be the same. Okay. So these are independent events. What happened on the first draw, by replacing the tile, these became independent events. What happened on the first one has nothing to do with what happened on the second one. Now let's compare that to looking at when we pull out a tile, that tile is not replaced before we do the second draw. Okay, so the first draw, we know that the probability of getting blue is 2 out of 4, or a yellow is 2 out of 4. Okay. So now we look at our second draw, and our bag has changed. This one has not been put back in. So our bag has changed. Now one of the blues is gone, so we're only left with one blue and two yellows. So that is going to change our probabilities. Well, on the second draw from this bag, there is only one way out of the 3 tiles to get a blue. For the yellow, there are 2 ways out of the 3. Okay. For the second draw, if I had pulled out a yellow in the first one, then it's gone. So the only thing left in the bag are the 2 blues and the yellow. So the probability of drawing a blue is you have 2 opportunities out of 3. The yellow is 1 possibility out of the 3. Okay. So our second draw becomes the probability of the second draw given the first draw. Okay, so let's go ahead and list our probabilities and see what happens based on these outcomes. So we have 2 over 4, 2 over 4, 2 over 4, and 2 over 4. So that is for our first draw, whether we get a blue, a yellow, or a yellow. For our second draw now, notice these have changed because their probability depends on what happened on the first one. So this is times 1/3. Our probability on the second draw here was 2/3. This is 2/3, and this is 1/3. Okay, so if I do my multiplication on this, I see that this is 2 over 12, which is 1 over 6. This is 4 over 12, which is 1/3. This is also 4 over 12, which is 1/3. And this is 2 over 12, which is 1/6. So you can see by whether or not you replaced the tile or you did not replace the tile, changes the probability. Not replacing the first tile changes this to dependent events. Now, just to help clarify this, I always like to do little shorthands for this. Dependent events when you're drawing tiles would be without replacement. If I go back up to the first page when I'm looking at independent events, this is with replacement. Okay. So let's see what we can do here now. Alrighty. Suppose whoops. Actually, I think I'll start a new video here because we're right at a good stopping point and we're starting a new topic. So I'll be back in a minute.